Roman numeral 3 is on rotary motion. We will be looking at objects that are rotating about an axis. And then we're going to use some of the terms that you've already studied, such as displacement, velocity, and acceleration, and show how they can be translated into something that's moving. So we're going to start out with a radian. And if you consider an object rotating about its axis, during one revolution, it's going to travel a distance equal to the circumference of the circle, which is 2 pi times the radius. And a radian is defined as half pi of a revolution. We will be using radians in the next section, but you will not have to change anything on your calculator, so you don't have to switch to radian mode. You can keep it in degrees. And if we go back and look at the circumference of a circle, instead of saying 2 pi r, we can define it also as 2 pi radians, and the abbreviation for radian is going to be a rad. They don't have any units. Okay, radian is considered to be your unit. You do need to know the equivalent of how to convert from degrees to radians, so you can use these two conversion factors and set up a ratio. So 180 degrees would be the same thing as pi radians, or pi rad, and 360 degrees would be 2 pi rad. So for example, if I wanted to find out how many radians are equivalent to 40 degrees, I would say 40 degrees is X number of radians, and that's equal to, we'll go with 180 degrees, and that's equal to pi radians. And you would simply cross multiply and come up with your answer in radians for the equivalent to 40 degrees. For the next part, we're going to look at angular displacement. It's defined as the change in the angle as an object rotates. Don't forget your book has a really good picture, so I included those in your notes. On page 198, you can look at figures 8.1 and 8.2. And if we think of having a circle, you know what the radius is going to be. Well, if we look at the radius at two different locations, such as to here and to this point, there is going to be an angle between those two radii, and distance is going to be defined as that arced section of the distance of a circle. So if you were to take a string and place it around a circular object, and then take that string and flatten it out and measure how far it is, that would be our normal distance or displacement. What we're interested in is going to be the rotary version of that. So we're more concerned with the angle instead of the physical distance. So when we look at angular displacement, that's going to be the change in the angle as the object rotates. And usually you've dealt with that in degrees before, but I showed you on the last slide how you can convert those degrees to radians. We can also relate the angular displacement, which is theta, to that regular displacement, which would be the arced section that you see along a circle, where we talked about putting a string around it and actually measuring that distance. For the rotation through an angle in radians, at a point distance r from the center, you can relate the regular displacement and the angular displacement with the formula d equals r theta. For angular velocity, we've had velocity before, and it was simply displacement over time, or distance over time if you did the scalar version. The symbol for angular velocity, however, is going to be this curvy W, and it's the Greek letter lowercase omega. And if we look at the definition of angular velocity, it's the angular displacement divided by the time taken. So if we go back to our normal version of velocity and replace it with the Greek letter for omega, instead of saying regular velocity, we would now have angular velocity, and then equals. Instead of regular displacement, you can have angular displacement, and then simply divide by time. It's the same formula you've had before. We are just replacing our letters with some from the Greek alphabet to indicate that something is moving in a circle. So anytime you see that word angular, that means that the object is spinning and it's moving around about an axis. You can relate the linear velocity, which is the normal one that we've done before, a distance r from the center, which is going to be your radius, and relate it to the spinning angular velocity by the formula v equals r omega. For our next slide, you can also relate angular velocity to something called the frequency. And for this one, sorry for flipping back and forth, if we rearrange the angular velocity formula for v over r, okay, that's going to be this first section of the formula. Okay. And then think back to when we did the centripetal acceleration lab, where we looked at the distance once around a circle as being 2 pi r, and then dividing it by the time, okay, which was the period once around the circle. Well, if we're talking about radians, that r is simply a rad, and you can leave it off for our formula. The period, the t, is going to be once around a circle, and then we have this new term, frequency, that's defined as 1 over the period. And we're actually going to study that a little bit more in the second semester when we talk about waves. But for now, I just wanted you to be introduced to it. The version of angular velocity that will be required for you is going to be the angular displacement over the time, and then linear velocity over the radius. When we talk about this version with the period and the frequency, these two are going to be bonus for you. And then hopefully you remember that regular velocity was measured in meters per second. For things that are spinning, we're going to replace meters with radians. So that means our angular velocity is going to be measured in radians per second. And then don't forget your displacement is radians, not degrees, and that's taking the place of meters from the things we've studied for the linear version. And then our last equivalent that we're going to do is angular acceleration, and it gets the Greek letter alpha, which is the funny little fishy. The definition for angular acceleration is the change in angular velocity divided by the time required to make the change. Now think back to acceleration when we studied things that are moving in a straight line. Before, we had said that acceleration was change in velocity over time. Well, the definition for angular acceleration is pretty much going to be the same thing. We're going to replace our regular a with alpha. It's the Greek a, and that lets you know that something's spinning in a circle. And you should know by now that change is going to be delta, and angular velocity is that curvy little w called omega, and then divide by time. I hope you're seeing a pattern that we're taking the same formulas we've already studied for things that move in a straight line, and we're just giving them new letters to show and indicate specifically that they're moving around in a circle. And then just like the other versions of displacement and velocity had for an angular equivalent showing how it relates to the linear version, angular acceleration has the same thing. So linear acceleration, that's the normal one, the plane A that we've studied before. So if we look at that, it can be related to the angular version or the spinning version by multiplying radius times alpha. And instead of meters per second, it's going to be measured in radians per second. And then our last slide shows you a summary. If you had a little bit of difficulty following before, I would study this page. Okay, I tried to summarize for you in the data table things that we've already studied, which would be displacement, velocity, and acceleration. The linear version is what we've had before. Displacement is in meters, velocity is in meters per second, and acceleration is in meters per second squared. And then we have the formulas here as well. I did leave off the delta on the acceleration version, so if you wanted to replace that in your notes to indicate the change in velocity, you can do that too. The angular version is for something that's spinning. So before we did things that move in a straight line, and then today we're looking at objects that are rotating about an axis or spinning. So when you see that word angular, think in your head something that's spinning. So we're taking our d from displacement and replacing it with theta. The meters gets replaced with radians. For velocity, the v is replaced with omega, and instead of meters per second, it's radians per second. Our acceleration, the plane A, is replaced with the Greek version of an A, alpha, and instead of meters per second squared, it's radians per second squared. And so in this column, we have the angular equation equivalent to the ones we've already studied. Velocity was displacement over time. We're simply adding the word angular in front of those terms. So now angular velocity is angular displacement over time. And instead of acceleration being change in velocity over time, we have angular acceleration is change in angular velocity over time. It's the same concepts that you've had before, we're just giving them new letters to show things that are spinning instead of moving in a straight line. And then finally, this last column shows you the relationship between the linear version, the plane D, V, and A for displacement, velocity, and acceleration, compared to the angular version, the theta, omega, and alpha. I will also be adding example problems that I'm going to post to Google Calendar, so hopefully that will help you out when you go back to study your homework and try those problems. Maybe you can find an example that will be worked in the same way so that you can understand how to apply these formulas.